Before we move to the last topic of this class, which is the last criterion of stability, let's just see how we can do the same exercise by the use of MATLAB, which of course makes everything simpler. So we just have to define, as we've seen previously, the s variable as the Laplace variable with this command s equal tf of s. Then we can just type the transfer function h just by writing down the literal expression in this way. Once this is done, we can compute the closed loop transfer function by employing the closed loop formula that we've seen before. So k times h at the numerator and 1 plus kh at the denominator. So we will pick two different numbers of k. We'll pick first value of k 100, which will make the closed loop function stable, as we've seen previously, and k equal 2000, which will make the transfer function unstable. So that's the closed loop transfer function. So the closed loop function is given by this formula over here. I add this command mean real, which basically means that this expression has to be simplified, something that you would have to do also by yourself in case you do the computation by hand. And so there we go. This is the first transfer function from c to y in the case of k equal 100, which we have seen according to the Routh-Hurwitz criterion was stable. So how do we check this by MATLAB? Well, we can just compute the roots of the denominator with the command pol, which of course is done by a computer. It's easy to do. So like this, we don't need to run we don't need to do the Routh-Hurwitz criterion at all, because we already have the answer. So we just check. As you can see here, the real part of the roots is negative, so this is a Bibot stable system. Let's see now for F2. In the case of k equal 2000, you might remember this corresponded to an unstable system, closed loop system. So let's check the poles of F2. And there we go. We have two poles which have a positive real part, meaning that the system is genuinely unstable. That's it. So you see why I said that if you have a computer, you don't really need to know the Routh-Hurwitz criterion, and that's why this criterion is taught more as a sort of legacy with respect to older times. If you wish, you can actually download from MATLAB Central File Exchange a nice MATLAB script that will do the Routh-Hurwitz table for you, which you can use in case you want to put yourself to the test and see if you've done it right or wrong with all the transfer function that you wish. You can create any exercise you wish by just typing any transfer function, do the Routh-Hurwitz criterion, and then check it with this function over here. Very well. So let's move now to the last stability criterion which we are going to see. I call it in this slide the Bode criterion, but actually you will probably not find this name in the literature. If you look at the French literature, you will see it appearing as critère du revers, which means the inverse criterion, the reverse criterion, the backside criterion. I really don't know where this name comes from, but remember it in case you look for it, critère du revers. And in the English literature, you probably see the general version of this criterion, which is called Nyquist criterion or Nyquist theorem. This one that I call Bode criterion is a simplified version of the most general Nyquist criterion, and which is the one that probably is most useful in the practice. And we do not look into the details of how and why this criterion works, but we just look at how to apply it. And actually it is very useful and very practical. Just the first remark that you have to pay a lot of attention to is that the Bode criterion is a different criterion with respect to the one we have seen before. The criterion we've seen before were related to a transfer function with a given expression. So I give you h of s from a signal to another signal. You have a numerator, you have a denominator, you have three criteria, basically looking at the input response, okay, if you can compute it, but otherwise the most important criterion is looking at the poles, the roots of the denominator, and then you can know if this function is bifostable or not. In case you cannot compute the poles directly, then you can use a root or Swiss criterion, which gives you an answer still for h of s. The Bode criterion does not involve a transfer function alone. It involves a interconnected system like this, which is a special case, of course, but it is the most interesting special case that you have in control systems, because it is the typical feedback loop interconnection. So basically the Bode criterion will tell you whether the transfer function from C to Y is stable, starting from consideration from D and R, without the need of computing the function from C to Y explicitly, which is this one. So basically, say it again, the Bode criterion will tell you whether this transfer function here, D over 1 plus RD, is stable, without the need of computing it, as we did in the MATLAB example, for example, just right now. You don't need to compute it, as I say, you just need to look at dr, namely you need to look at d times r's Bode plot. That's why I call it Bode criterion, or Nichols-Black plot. So just pay a lot of attention to the first bullet over here. This method allows evaluating the stability of closed loop systems, like this one, which means, in this case, y over c, from c to y. Okay? So the important point, as I said again, let's read again to make sure we got it. You can determine the stability of y over c as a function of L, which is d times r, without need of computing explicitly y over c. Okay? Last remark, it applies only if L has no poles with strictly positive real part. This doesn't mean that L has to be bifostable. It means that there are no poles with strictly positive real part, because you might have a function which is not bifostable or even unstable, that only has zero real part. But still, the criterion can be applied. What rules out the use of the Bode criterion is the existence of poles in either D or R, which means in L, RD, which have a strictly positive real part. Okay, so the proof is complicated. It relies on what's called the Nyquist criterion. You can look for it if you like in the literature, but we skip it here for lack of time. We just give you an intuition of, let's say, not really why it is true, but an intuition that it makes sense to look for what we are looking at when applying this criterion. So just look at this function over here. So you know that the closed loop transfer function from C to Y has at the denominator the term 1 plus L. I call the L the loop transfer function. And you might notice that if L equal minus 1, then this thing blows up. 1 plus minus 1 goes to infinity. So basically you can imagine that a signal C will yield a signal Y that blows up. So for this reason you can imagine that the point L equal minus 1, so if L assumes the minus 1 value, which is equivalent to 0 dB and phase minus 180, this point has a special meaning with respect to the Bode diagram or the Nichols-Black diagram. And in fact, we call this point the critical point. And this point is usually visualized into the Nichols-Black diagram. So let's see again the example we just seen beforehand. This time we'll use the Bode criterion. I didn't tell you the Bode criterion yet, but let's just see the different values of K, what they yield in terms of L, in terms of loop transfer function, and in terms of its Nichols-Black diagram, and how the Nichols-Black diagram behaves with respect to this critical point, minus 1 in terms of a complex number, or 0 dB minus 180 degrees of phase. So if we take k equal to 1, you remember we have a bivostable system, and we have this Nichols diagram here. And you can see the critical point is at the right hand side of the diagram. Okay, remember the curve has an orientation. It has a, say, a one-way sense direction of traffic. So imagine you are walking along this line or driving your car along this line, you see the critical point at your right hand side. And in this case we are stable. So let's try again. K equal 100. You see this one changes. What changes basically from k equal 1 to k equal 100? I remind you, this is the Bode chart of L. L is k times h. So if you go from k equal 1 to k equal 100, basically you increase to order of magnitude corresponding to 40 dB up. So basically the curve is shifted 40 decibel up. So shifting the curve 40 decibel up, which correspond k equal 100, then you still have the critical point at your right hand side. Now if you pick 108, which is the limit, if you remember, you can see that actually the curve goes through the critical point. And in fact, in this case, we have a function which is not bivostable. It is on the margin, let's say, of stability. It is a critically stable system, which is not stable. And if we go beyond this k, then you will see, for k equal 2000, for example, the point is at the left hand side of the road of the Nichols chart, and this identifies an unstable closed loop system. So pay attention to what I said here. From k to h, the function k times h is always the same. It's just shifted by some k term, and it is always stable. We have seen previously that all the poles have a strictly negative real part, so we can apply the Bode criterion, by the way. So the changing of k doesn't change the fact that h is stable or not. Okay, imagine this signal is called u. The transfer function from u to y is always stable, always bivostable. What we are looking into is from c to y, and this transfer function from c to y changes according to k. And so, as we said beforehand, the Bode criterion, just by looking at the Bode diagram of k times h, of L if you wish, allows you to decide whether from c to y the system is stable or not. Okay, pay a lot of attention. This is not the Bode diagram, the Nichols diagram of y over c. This is the Nichols diagram of L, which is k times h in this case. So you can also look at this Bode criterion in the Bode diagram directly. Let's look at the case of k equal to 1. The idea is very simple. You can basically translate the consideration of the Nichols chart into consideration of the Bode diagram. Basically, you can read it here. The idea is that instead of looking whether you are at the right hand side or at the left hand side of the Bode diagram, you just check for all the values of omega at which your transfer function has a minus 180 degrees of phase, or minus 180 plus any multiple, an integer multiple of 360. What should you have? You should make sure that the gain, the magnitude of the Bode diagram, is smaller than 0 dB. Let's see why this is true. Well, it's obviously when you hit this line over here, right? If you are over 0 dB, it means that the point is on the left hand side of the diagram. On the other hand, if when you hit minus 180 you are at less than 0 dB, then the point is obviously at the right hand side. So that's it. So if the system is closed loop stable, if and only if for all these values of omega the modulus corresponding to it is smaller than 0 dB. And let's see, for example, over here, we just hit minus 180 degrees here, then we check the gain. There you go, it's smaller than 0. So in this case, again, for k equal to 1, we have stability, closed loop stability. Again, for 100, we do it again, minus 180, climb up, check, we are below 0, stable. Again, k 1008, sorry. You see, in this case, for minus 180 degrees, the same, just look up the same angular frequency, you see we are exactly 0, so we are in the critically stable case. And then if you go to higher values, k equal 2000, then you see for the omega, which hits minus 180 degrees, we have a value of magnitude that is bigger than 0 dB, which means unstable. I repeat, from C to Y, H is always the same, doesn't change with K. H is always stable. Very well, so now we are ready to formulate it. You might have got it already. So the Bode criterion concerns closed loop systems like this, a structured system like this. It allows you to determine whether the transfer function from C to Y is stable as a function of d times r, which we call L. Pay attention, negative feedback. Okay, negative feedback. It can be used if the transfer function, loop transfer function L, has no strictly positive real poles. Zero real pole, zero real part poles are acceptable. So what the criterion says, Y over C from C to Y is stable, BIBO stable, if and only if you have three equivalent statements. So the first statement, which we've seen first, the Nichols plot of L of S leaves the critical point at its right hand side, or for all the values of omega where you hit minus 180 degrees plus multiples of 360s, the modulus is always smaller than 0 dB, or equivalently, this is a bit more tricky, but you have to pay attention. So if your Bode diagram is always smaller than 180 degrees, then you can look at all the omega for which your modulus is 0. The phase in these points, in these frequencies, has to be greater than minus 180. By the way, remember this value, omega c, is called crossover frequency or crossover angular frequency. It is basically the places where the gain, the modulus of the Bode diagram hits 0 dB. Usually it is only one place, but it could be more than one. So I hope this is clear, and now we see some examples. There are several examples, and I will leave you the time to think of the answer, and then you will check. You will be able to check the solution with me. So please feel free to stop the videos just before the answers. First example. So we consider this closed loop system over here. The question is whether the transfer function from C to Y is BIBO stable. Of course, we have to answer without computing this function and computing the pole, so applying the Bode criterion if possible. The function is the one given over here. So these are the Nichols diagrams and Bode diagrams. Solution in 3, 2, 1. Okay, taking the Nichols diagram, well, the difficult thing is finding out which is the orientation of the diagram. By thinking at the Bode diagram, you can clearly see that it comes from plus infinity of magnitude. So this is the beginning of the diagram, so it goes like this from top to bottom. So the Nichols chart leaves the critical point at its right hand side, and do not forget also to check that the transfer function has no strictly positive real poles. There we have 0, -1, -10. Okay, no problem. Then we can check also on the Bode diagram directly. So you remember there are two ways: either check -180 for this omega O, I call the angular frequency where you strike -180, or the -180 plus the multiples of the 360 degrees, but there aren't any here. Check whether the gain is smaller than 0. Here it is, so again BIVO stable, no problem. Or otherwise check the crossover frequency, omega C, where you hit 0 dB in case your diagram is always smaller than 180 degrees, which is the case over here. Then check down here, is the phase greater than -180? Yes. So again, BIVO stable. The three expressions are equivalent, so of course we get always the same answer. Next example, same kind of situation. Now we have a slightly different transfer function. These are the diagrams. Solution in 3, 2, 1. Well, in this case we are unstable, so the transfer function is just the same as before, with a bigger gain, which corresponds to a curve shifted up of 60 dB, if I'm not wrong. And now the critical point is at the left hand side of the Nichols diagram. And again, let's do the other checks. For -180, you can see the gain is greater than 0, and for 0 dB crossover frequencies you have smaller than 100 -180 degrees. The phase is smaller than -180 degrees. So unstable. Next, simple transfer function. Solution in 3, 2, 1. A pole in S equal to -1, so strictly negative, no problem, it can be done. Looking at the Bode diagram, you can see that it comes from -40 and goes to -infinity, so the orientation is this one. The critical point is at the right hand side. And let's check also on the Bode diagram. We never hit -180 degrees, so we are basically okay. Or otherwise, we hit 0 dB crossover frequencies here, and it is for -90 degrees of phase, which is greater than -180, so we are fine. So pay attention to this case over here. If your phase never hits -180 degrees, and also 180 degrees positive, so it's always between 180 and -180, well, regardless of what the gain does, the closed loop system is always stable. For example, another transfer function over here. Solution in 3, 2, 1. Well, this was a little bit of trick. We have a positive real part pole, S equal 10, so the Bode criterion does not apply. What should we do in this case if we want to check the stability from C to Y? Well, we should have to compute this function and then compute the poles, or use Routh-Hurwitz criterion as a last resort. Very well. A last notion which we are going to see today is the notion of the margin. So what means the notion of margin? Well, it just try to quantify a little bit more the notion of stability in terms of not only giving you a yes or no answer, is the system stable, BIVO stable, yes or no, in closed loop, but also tell you how far it is from the condition which would bring it to instability. So basically the margin tells you how far you are from becoming unstable, in the case you are stable, in the case your closed loop system is BIVO stable. So these margins are defined with respect to the Bode criterion, the Critère du Levert, and so they apply only for closed loop system, and namely they apply just to the quantities we look into when we are assessing the stability of a closed loop system by using the Bode criterion. There are many of them. I provide you a list. We just look at the first two, the phase margin and the gain margin. So what is the phase margin? Well, if your system in closed loop is bivostable, it means that at the crossover frequency the phase is greater than minus 180. So the distance between minus 180, the phase for which you would be unstable, you will start to be unstable, and the phase that you have is your phase margin, which is basically visualized here. So what is the phase margin? Is the amount of phase you can subtract from the loop transfer function before the closed loop becomes unstable. Okay, look at this example over here. At 0 dB you have minus 135 degrees, so you are okay. Imagine you lose 45 degrees, then you are not okay anymore, because you would hit over here. So you have 45 degrees of phase margin, positive 45 degrees, so because it is the amount of phase you can subtract. So a positive phase margin means that the system is bivostable, and the amount of positive margins you have is the amount of phase you can remove, you can subtract before going unstable. This is what is written here. If no point strikes 0 dB, then by definition we can say the phase margin is infinity. Second definition is the gain margin. So what we said when we look at both the criterion, you look at points where you hit minus 180 degrees, and you have to make sure that your gain is smaller than 0 dB. So in this example over here you have minus 20 dB, so you are safe. It means that if your function grows up, you can still grow up of 20 dB before you hit the critical point, let's say, and before you become unstable. So basically the gain margin is the amount of magnitude of gain that you can add from the loop transfer function before the closed loop becomes unstable. Again, a positive gain margin means that your system is stable, a negative gain margin means your system is unstable in closed loop. Pay attention, by the way, that this is one of the definitions we provide, but in the literature you might see something slightly different. Again, as in the previous case, if there is no omega O for which you hit minus 180 degrees, then the gain margin is infinity by definition. These margins are actually very easy to see in the Nichols chart. Actually, imagine your line is your blue line here is the true Nichols chart of a function. So you see the critical point is at the right hand side, so you are stable in both cases. So what is the gain margin? In this case, you see the gain you can add before you hit the critical point, this line over here. Phase margin, the phase you can remove before you hit the critical point, this line taken with a positive sign, even if it goes leftwards. Very well, let's now review the previous examples as before and try to see if you can provide, if you can figure out which are the margins just by looking at the picture. Of course, we don't expect precise value, just see if you can provide an approximate answer. So solution in 3, 2, 1. Well, just zooming in a little bit, if you can read it, this was a first example. We had a closed loop stable system, so you can look at the Nichols chart over here. For 0 dB you hit more or less minus 135, so the phase margin is 45. From minus 135 to minus 180 you need 45 degrees less, so phase margin 45. Gain margin, well, you hit minus 180 degrees more or less at minus 20 dB, so you have 20 dB gain margin. You can see the same quantities over here in this picture here. Let's go to the next, second example. Solution in 3, 2, 1. Well, this was an closed loop unstable system, so both margins are negative. You can read them here in the diagram if you wish, or over here. Third example, solution in 3, 2, 1. This was a closed loop stable system, so let's look at where you hit 0 dB. It was more or less at minus 90, so you hit at minus 90 means that you can still lose 90 degrees, so you have phase margin of 90 degrees. Where do we hit at minus 180? Well, this curve never hits minus 180, so by definition your gain margin is infinity, and you can see it actually like this. You can increase the gain as much as you want, which means sliding this curve up, 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 up forever. You will never hit over here. By the way, these kind of results, be aware, be careful, are purely academic, in the sense that this model, this transfer function written on the paper, can have an infinite gain margin, but in the reality, well, you will never have a real system that has a really gain margin. You probably should consider a more complex model before assessing this. Last example, well, solution in 3, 2, 1. If you remember, this example was a tricky one. There is a real positive part pole, so both the criterion does not apply, so we cannot define margins over here. That was it for today. I hope this was clear. Thank you for listening, and everybody please stay safe.